Okay, welcome everyone. So who here cares about performance and gets involved in the arguments of C++ versus Java or C# versus C++, all of this sort of fun? I spend a lot of time in this space, and I work in finance quite often, helping people trying to make systems particularly fast, and often people will get me in, they'll help the C++ team, sometimes the Java team, sometimes the C# team. And I often get asked this question because people kind of say that I'll program in multiple languages, but they'll say, really, what's your preferred language if you've really got the choice that you'll program in for high-frequency trading? And we need to be pretty fast in this. So, like, could be building financial exchanges, could be building trading systems, could be doing something like that. And whenever I tell them the answer, this is the sort of result I normally get from people. They kind of looking at me going like, really? Java? Why not C? Why not C++? And if I sort of say, well, yes, Java, and I'll get around to explaining it, it's usually very quickly followed by this question. But it's low latency applications. What if you're building on a garbage collected platform? Is this really a good idea? And at this stage, there's usually some older C programmers in the room. They're sort of around about the same age as me in some cases. And they'll tend to look back at me like this. I think it's an incredible level of stupidness, maybe. So let's kind of explore this and see, is it really the case? Is it stupid these days to build on managed runtime? And by managed runtimes, not just Java. So mostly people here are probably doing Java, but sort of C# and even other platforms, like crazy platforms like JavaScript. These days you can do quite interesting things. So first up, I'll start with some context. And part of that is, let's be clear that it's not always the absolute right choice to build on a managed platform. And why is that? So let's take a simple example. So if you're going to do a thing called latency arbitrage, so in the finance industry, latency arbitrage is where you want to be the absolute fastest in a market. So if an opportunity arrives, you're going to react, and you're going to react faster than anyone else. If you're in that space, actually, any language that you're typically writing in is not the answer, because a lot of this stuff is done in hardware, typically in an FPGA ASIC that runs in the network switch itself, right next to the exchange where the trading's happening. So it's kind of a bit of a mute argument in this. So what we're talking about is things that are outside of that, where they're a bit more complex. And also going to explore this, well, if I'm using a native language, is the native language really the thing that's going to be faster? And I'll kind of say up front, to be honest here, like if you look at a situation and you have got infinite time, infinite access to the best people, and infinite resources to work with, yes, you can make things ultimately faster in C, for example, than you can in Java or C#. But there's a big but. You need to have access to all of those different things. We'll kind of explore the difference that comes out from that. So for context, I want to sort of focus this in on things that involve instructions that we have running on CPUs accessing memory. I'm not going to go into the space of, well, if we're using networks or we're using storage, because that's a different case. And often the choice of hardware is a much bigger influence than the choice of language that you've looked at. So we want to look at like sort of side by side. We have something that's computationally intensive and it's running in memory. So let's start off and set some interesting positions up here. So if we want to add two integers together, like how fast can hardware do this? And then look at, well, how does our languages fit on top of that? So answering the question, how long does it take to add two integers? And these are two integers in registers at a given point in time. Anyone know? 1 cycle. Yeah, that's it. It only takes 1 cycle to do this for two integers into registers. And you'll find that many of our instructions are very much like that. It's a very short space of time. Like if you're running on a 3 gigahertz CPU, that's only 1/3 of a nanosecond to do that. So that's an incredibly tiny amount of time. Now let's make this a bit more of an interesting problem. Let's say I want to go through a whole array of integers, like a gigabyte's worth of them, and I want to sum up all of the integers in that array to have a sum as a final value. What is the time going to be for each individual step in that. And so each step is going to be like, so read a value, increment the scalar that we've got that's running as the summation so far, and continue on to the next element in the array. So per step, what is the time for that? So if we're going to have some good science, let's measure it. So let's write a test to do that, and we'll measure it and see what results we get. So if I do that across a 1 gigabyte array, I find out that my average time per operation of doing that is 0.8 of a nanosecond on a 2.4 gigahertz CPU. So that's kind of interesting because you start thinking about it. Hang on, I said before it was one cycle to add any given integer. Yeah, so we're doing a bit more than that. We are adding integers as we go, but we're also incrementing a loop counter. We're loading that memory into the CPU registers, and we're storing the result back of the summation as we go. So there's a bit more work to that. So you start thinking, like, really less than 1 nanosecond per operation when there's like quite a few instructions to this. There's like around about 10 instructions per step in doing this. So how do we do that number of instructions in such a short space of time? And that is because our modern CPUs do not have a single ALU, single arithmetic and logic unit. They have many. So this is a Haswell, which is a CPU that's been around for quite a few years now. And you'll find that there's actually 8 ports on the scheduler that's inside a core. This is not the operating system scheduler. This is the scheduler inside a CPU core. We have 8 ports on that, and 4 of them can be doing mathematics at the same time. The others can be doing things like branching, like loading memory from our cache subsystem into registers and writing it back from registers to the cache subsystem. So it does a lot of things at the same time. We have concurrency going on even within our single threads. And you start thinking, well, how can that happen on a single thread? But take, for example, that simple loop that I'm talking about. I'm going to go across an array. I want to add up all of the integer values in the array. I'm incrementing the loop counter. I'm incrementing the summation of what's going on, and I'm loading and storing. There's a certain amount of dependencies, but there's also a lot of opportunity for parallelism in that. Like, I can be incrementing the loop counter at the same time I'm also incrementing the summation of what I've added up so far in the array. So that can happen at the same time. We start to get significant progress through this. In fact, we could have vectorized that, but that's a different subject. The JVMs, mostly that we have at the moment, do not vectorize where the target is a scalar. It only vectorizes where the target's a vector. So a hotspot working that way, but other JVMs can do that, and we're going to start seeing that with future generations of it. So we can be doing multiple things at the same time. But a much more interesting question: what if our access pattern to memory is different? I had a really simple access pattern there. We're going to go through the array completely sequentially, touching every element in the array and adding them up. What if I was a bit more random in my access behavior to that, like jumping around within an operating system page, jumping around across the whole array, or even get a bit more twisted, where the next step that I take in the array is going to be dependent on the previous value that I've just read. These sorts of things can really change it. So what I want to do now is let's look at the different patterns of access, and if I take those patterns of access, see what impact they have on the overall performance, but where there's roughly the same amount of work happening in each of these cases, the only difference is the patterns of access. Now, these are the different figures we get if we run some different patterns of access. So what are those? Well, there's the sequentially going through the whole array. There's going random within an operating system page, touching all of the different elements within that page, then moving on to the next one, doing the same again, moving on to the next page. We can go random around the whole heap, where we're not just staying constrained within an operating system page. And the dependent ones are staying random within a page, but having the next step dependent on the value you've read in the previous step. We start to see there's quite a difference. We go to 2 orders of magnitude of difference. So what's going on there? Why is some of this stuff different? Well, if we stay within the operating system page, we benefit from a thing called the translation look-aside buffer, which is a small cache that does our virtual to physical address mapping. So every time we touch a piece of memory, we program in a virtual address space, but our hardware is working with physical addresses. So the virtual has to be translated to the physical. It's a very small cache. If you're staying within the same page, you're benefiting from that cache. What's happening with the dependent versus the non-dependent versions? Well, we actually find that our L1 cache can track 10 concurrent cache misses at a given point in time, so it can keep going ahead and making progress. Our CPUs are very complicated. They're known as speculative out-of-order execution engines, and what that means is they will keep making steps forward even when they don't know the current state of the world, provided they can predict where they're going. And the one thing they can't do to predict going forward is following from one address to another address where they haven't resolved the first step to go to the next one. That sort of pattern, we'll hear it termed as data-dependent loads, or you'll also hear it as pointer chasing. So chasing pointers is by far the most expensive thing you can do on CPU today. And that's when you go to access memory. So it starts to become quite clear when you profile these things at a low level that the cost of instructions for most applications it's not a factor that matters. It's a rounding error in the grand scheme of things. The thing that really matters is the number of cache misses you have, and particularly cache misses that result in data-dependent loads. Like simple examples of where one would apply, where the other wouldn't apply. Going through an array list in Java is very fast to iterate. Going through a linked list in Java is incredibly slow to iterate. If you measure across a large data set, there's about 2 orders of magnitude difference in your iteration time. These things start to really make a difference. So with that context, let's look at what the runtime can do to make some of this better for us. I want to look at it from a couple of different perspectives. But kind of first up, what can a runtime do that a static compiler struggles a little bit with? And one of these things is a thing called profile-guided optimization. So our compilers can do a lot of optimizations for us. They do pretty amazing things. But one of the things they can do that's very nice is if they know your data and your access patterns, they can do a lot more than they can with just a static view of your code. And we'll show some examples of this. The cool thing is with a runtime that's taking this data from your real application is it can specialize the optimizations to what you're doing. A static compiler can't do that. It has to make some generic optimization choices, and they may or may not work for your real application. Now, we have means of taking static compilers and we'll produce a build that will collect data, and that data can go back into recompiling your code again. We can do this in C and C++. It's not a very common thing for people to do. And also on top of that, it's very hard to create the right data set that will generate the right optimizations for us later. So it's a really tricky problem to address. Our runtimes are in a much better position because they've got the real data all the time and they can deal with it. So they can approach this in a different way. But even better than that is they can have a bet and they can make an educated guess to what is the right thing to do. And if they're wrong, it's okay. They can go back again, they can revert these changes, and they can go and do it in a different way again later. Static compilers will struggle with that. They don't have that sort of advantages. So let's look at some concrete examples. So simple little piece of code here. I've got a method foo. It's got some code at the top of it. It's got a condition in there. There's some code inside the condition, and there's some code at the bottom. If we were to compile this up, we end up with a number of blocks of code in here. Right, we've got the beginning block of code where we're going to run the top of it, and then we're going to run the if condition. Now remember this thing about if we can go sequentially through memory, we're much faster than if we walk around randomly through memory with any sort of random or arbitrary pattern. It's better to go through code sequentially. So then we hit the condition, like, is this a common condition? Is it not a common condition? We're in there. This may not be a common condition, Like good examples of this would be if you're writing your code and you write it nicely by programming by contract, so you check all of your arguments. If your arguments are correct, you can progress. If they're not correct, you'll throw an exception and not go forward in your code. Kind of good coding style, but you're going to assume that the majority of the time those branches will not be taken. You will not go inside the ifs to execute that code. You'll be jumping afterwards. So you would go to block A, you jump over block B, and then you do block C. That's not a linear access pattern if this is an uncommon branch. If it's a common branch, so you typically do go into that if statement, you just go straight through, and that will be really fast. So you kind of get this interesting one. Is it going to be common? Is it not going to be common? Well, in native languages, we can hint these things, and if we're right, the compiler will lay out the code in the optimal way. If we're wrong, we'll actually end up with the wrong results. And on a very large code base, it's really hard to get this right for every one of your branches. So it becomes a really interesting challenge. But if our compiler gets data to do this based upon our runtime performance, it can generate the right code. So it may just do block A, follow it immediately by block C, and then have block B somewhere else off in memory because it's uncommon in its usage. In fact, it may not even compile the code that's inside block B. It may just put a trap in that the interpreter can kick in, and it will execute that sort of code later. These sorts of things are becoming very common. So C# just this week had this added to their JIT compiler. It's available in other JITs and stuff. So very simple, very common ways we can lay out code driven by the runtime and what's going on. But sometimes our ifs and our branches are a little bit more obscure. You could have a condition like a ternary here. So it doesn't look like an if, but it really is an if at the end of the day to the compiler. And what we're looking at, if I is greater than 7, I'll assign A. Otherwise, I'll assign B. Now, this is a kind of interesting one, like which is the more common case? How would you hint it one way or another? What's even more interesting is, what if there's a different probability range to some of these things? So let's say I greater than 7 is like 99% likely. You could take a different approach than I greater than 7 being 50-50. Because if it's 50-50, you may not even lay the code out differently. You may choose completely different instructions. And on x86, for example, we have an instruction called cmove, which is a conditional move instruction that is not a branch. It's not treated as a branch by our CPU, which means it's not subject to branch prediction, and we get greater performance. But it's a little bit more costly than a branch prediction that's correct. But how do we know which is the right branch? Well, we measure our code at runtime and we discover that, actually, I'll be better off with this, I can go with that. If it discovers that I'll be better off just leaving it to normal branch prediction, it can also go with that. The runtime can make the right choice, do the right sort of thing. And these are the things that start to matter more than the individual instructions, because getting a branch wrong is usually about 12 to 15 cycles that has to undo it, and then you've got all of the associated cache misses to be heading a different direction through the code. What about our methods? So we have lots of methods in our code. The function call overhead is something that's relatively significant. So I've got a method again, foo. It's got some code in there. It's followed by a method bar, followed by some more code. How small is bar? Kind of interesting question. Well, what if I'm using it a lot? What if I just make it really simple? Well, I would typically have the code at the top, the code to call bar itself. I then take a function call, jump somewhere else in memory. I execute the code in bar. I then need to jump back and execute the code on the other side and continue on with block B. This is not a nice sequential path through the code. It's jumping around. That can occur a cache miss. It can slow us down quite a bit. But let's say bar is actually a very small method and it's worth inlining because this is a really hot method. So what we can do is we can have block AF code. We can just inline the code directly into this and get rid of the function call. So it's not even the fact that we'll lay it out sequentially. We can also get rid of the function call itself and follow it up with the following code on that. Now, this is a kind of really easy optimization for a compiler to do, but there's an interesting thing to consider here is how often should we apply it? So a static compiler could choose to inline quite aggressively, but what will happen is you've only got 32K of space in your L1 cache for instructions. You can end up overflowing that with code that's not important. So you only want to do this to the methods that's really going to give you the value. Like, how do you know in a very large application what are all of the right methods that need to be inlined? Well, if you're measuring your code at runtime and doing that, you can do it really well. Now, in C or C++, I can use the inline keyword, works a treat, but am I going to get it right? Am I going to judge that right in every case? I don't trust myself to do that. I know for some cases where it'll definitely work, but I don't know for every possible case. But we can measure this at runtime. It's one of the biggest optimization wins we can have, and trading off that balance between how much code bloat we have versus how much function calls we're willing to take to jump out of it, it really is an interesting one to play with. And you'll see micro benchmarks are not the way to drive this. I've seen so many cases of like, say you're compiling for C++ and use GCC, you can compile with -02 or -03. -03 is much more aggressive. It will inline code much more. It makes it look great in micro benchmarks, often makes a real world application slower because it's so large. It's got code bloat as a result. So getting the balance right is interesting. Cliff Click, who's one of the key developers of Hotspot and the C2 compiler around that part of it, he describes it as the optimization, like inlining, choosing where to do it, and then the resulting things you can do once stuff's inlined. Because the way compilers tend to work is they work with code blobs, and they inline a bunch of stuff together, then do a whole bunch of optimization decisions. They don't tend to do so much globally through your app. They tend to work in these nice local inlined areas. And if you've chosen to inline a nice piece of hot code, you can do other nice things like loop unrolling, like eliminating redundant code. All sorts of really interesting things can happen from there. Actually, I mentioned loops. Loops are one of the biggest things in your code that are good for targeting for optimization. There's lots of independent measurement that shows that we spend about 80% of the time in our code inside loops. But which ones? Which ones are worth optimizing? And what can we do about them? So at a very simple level, one of the optimizations we could do is loop unrolling. So if we were going to do the same thing, we can do it multiple times per taking the overhead of the loop cost. Because there's a lot more going on than just even checking loop counters. Depends on the type of loop we have. We may be doing checks to see, does the JVM need to come to save point for garbage collection? Maybe we want to do that once every 4 times, once every 8 times, rather than every single time. But we've got to do that, and we've got to do it in places that's going to give us value, because again, this is going to be subject to code bloat. But by doing this, we've got less jumps, less checks, and more sequential code. It works much nicer with our caches. Where do we pick these things? And we can also do really cool stuff once we get in to different levels. Like our compilers can apply these things called intrinsics. And what they're doing is they're looking for a pattern in our code. It's just a signature pattern. And based on that pattern, it can replace that code completely, often with a single CPU instruction. Simple example here, if you wanted to count the number of bits that are set in a given integer, that's a bunch of shifting and masking to do that. And if you look inside integer.bit count, you'll see there's a fair little bit of code in there. But if you're running on x86 and you're using this method really often, you can replace it with a single instruction called pop count. And that is available if your CPU supports SSE 4.2. We can determine this at runtime. Now, again, with the static compiler, I could compile to support this, but I need to know what CPUs I'm going to run on. It's not just that I'm doing a build for x86. I'm going to do a build for a certain processor on x86 that I know has got that sort of thing. Our runtime can just choose to go one way or the other based upon what it's actually seeing. And actually even eliminate all the checks that would need to be around that if you had written the native code to do that as well. So there's quite cool things that can be happening. Now, if we're writing in Java or C# or most other things, we often do polymorphism. So we deal with objects, we want to have method calls on those objects, and we want to apply some of our abstractions at this level. So I've got an array of shapes here, and I want them all to draw themselves. And so if I go to call draw, I don't know how many types I've got here. I may have one type. I may have two types. I may have many types here. What choices does the compiler have at this stage? Well, let's say I've got one type. Do I need to do virtual dispatch? Do I need to work out what type this is at runtime and call it, or do I just call the method directly, or even better, inline it into the code? But if I've got many types, I have to deal with it differently. So I have to use a virtual dispatch table if I've got typically 3 or more types, depending on the compiler implementation that I'm dealing with, which means I look up the type, I then indirect into a jump table, then I call the right code. That has a cost, quite a significant cost to there. And if you're writing code in C++, for example, it's one of the things I most miss if I'm writing C++ versus Java, is I have to use a virtual method, and I will always get a virtual dispatch at that stage looking at the code. Whereas the Java runtime can look at this and go, you know what, you've only got one type there. I can give a monomorphic implementation and call that directly, and possibly inline it. If you've got 2, it can still do stuff. It can do bimorphic. It can just put an if in its place. If you've got 3 or more, it tends to go to jump table. It treats it as megamorphic. Some JVMs, like this old JVM, goes up to 4 before it has to go megamorphic. V8 for JavaScript will go to 4 before it goes megamorphic as well. Like C# loses out here is it treats everything as final unless you make it virtual. Then it goes, even if you have one implementation, it will go megamorphic at that stage. So it depends on which runtime you're running on, the different benefits you can get. But what's interesting is this applies by call site, not across the entire code base. So if down here at this stage, I'm only applying this test for the type of shape, and that shape happens to only be a polygon, I can use the monomorphic version there. But maybe in the draw case, I'm dealing with 10 different types, in which case I'll do the megamorphic dispatch at that level. By having a different call sites, we can benefit in different ways. So again, it's not even that you have to do it all over the place. Whereas if you think about it from a C# perspective or from a C++ perspective, we've got to put virtual on something, and then it's applied everywhere that's used. You can't even specialize by call site. It becomes a different way of thinking about it. So how does the runtime deal with stuff like this? Well, it's dynamically loading our classes. If it's only loaded one type of that, it knows it's monomorphic. If it loads another type of that, it goes, hang on, this is new. I took a bet earlier. I took the bet that we only have one of those types, and actually for most of our objects, we only ever have one implementation of that type. Now I've got more than one. I can revoke my original decision, and I can go with a different approach and deals with it in a different way. And there's really cool stuff that even goes right back to Smalltalk, where we can do a thing called inline caching. So let's say I have 10 types of the shapes, but one of them is far more common than all of the rest. So let's say squares are far more common than every other shape. I can take the implementation for square and use it as an inline cache and do a vtable for everything else. So it can pay off in really interesting ways. These are things that have been around for a long time in some of our runtimes and work very, very nicely. So that's just an example of some of what our compilers can do. Let's look at the elephant in the room around garbage collection. So if you're going to do low latency, garbage collection is something that we end up worrying quite a bit about. I like to steal a quote here from Billy Joel, that only the good die young. And this is very much the case for our objects. If you want to improve the performance of your code, make sure your objects live for the shortest possible time. And this is all based on a concept known as the weak generational hypothesis. So some studies of code show that code that we have creates an object, it'll tend to be not alive after a very short space of time, and only a certain number of objects live for a reasonable amount of time. It's given rise to a thing called the generational collectors. So we treat things that are going to live very short amount of time different from things that live a longer amount of time, and the costs go up if we deal with things that live longer. As a result, we end up laying out our heaps in interesting ways. So we'll have a young generation and an old generation. Within the young generation, we're allocating in these T-labs, copying them through survivor spaces, and if they live long enough, they go to the tenured space. I'll come back to this in a second, but one thing to be worthwhile before getting into that is our hardware has got a lot more complicated than it used to be. We have these multiple layers of caches, all with different access times, different response times to deal with it, getting slower the further away we go from the CPUs, right out to memory, taking longer periods of time. But more significant than that is we have multiple sockets inside our machines, and these multiple sockets are connected by these buses that go across, or interconnects. Like QPI is Intel's type. AMD used to have hypertransport. They've now moved forward with a new type of fabric between these. But these add significant periods of time. We have distributed systems now in the same box. So where stuff runs starts to really matter. So you want to be working with memory that's local to your CPU cores that is running. If that memory is remote, it adds a significant cost. Like, that's kind of tricky for us to think about and reason about. Like, what can our runtimes do? And so, like, this is a kind of simplified view of the world. It gets worse than that. What if I drill down into just one of those CPU sockets, not even just into the machine itself? Within a socket, we have multiple CPU cores. Now, this is one of the latest Broadwell CPUs you can buy today. Multiple CPU cores, multiple cache segments, and separate rings. This is in the same CPU socket. It's highly distributed. If your threads are talking with each other and they're sharing memory within the same ring, it's faster than when they're going across to the next ring. It starts to really matter. So what does this mean for our applications, and what can our runtimes do to help us? Well, when we start allocating memory, you say new memory, what happens is your local thread ends up allocating memory from what is known as a TLAB, a thread local allocation buffer. And each thread has got its own TLAB that allows them to access memory quite efficiently. Now, where is the TLAB is an interesting question. Now, what we can do with some of our VMs is we can enable a thing called use NUMA on, say you're using the parallel collector within Hotspot. It will make sure that the TLAB is running local within your memory region, and so you're not going to take that indirection to elsewhere. Most people don't turn on some of these features. There's some really cool stuff that's available to us. What's a little bit unfortunate about some of that is it's not available to some of our other collectors. So like CMS and G1 don't have this sort of support. They're really going to need to develop this as we go forward, because our machines are going to be split up into many more different memory regions, and these memory regions become really significant to the performance that we end up dealing with. Our things have become much more NUMA aware, otherwise we're going to suffer, especially as we go to the new AMD machines. So things to be aware of is like, we need to have this locality of reference. It's really important, and we need to have this NUMA awareness within this. So if you're running on the throughput collector now, if you're using Java 8, try the use NUMA flag, and all of your allocations will be out of a TLB that's local to your memory region. In some cases, it gives you 30% performance improvements just by passing a particular flag. If you're using G1, you're kind of out of luck for now. Maybe you'll get that sometime in the future. What happens if your object lives longer than like just an iterator for a loop or something within a method? It needs to be claimed from that TLAB, and it needs to be copied into one of the survivor spaces. So this is part of like only the good die young. If you end up retaining it a bit longer, what happens is the GC has to find the objects that are still retained, copies them to the survivor spaces, and then starts over again with the next cycle for the new generation. And it goes around a pattern of repeating that over and over again, copying them multiple times between the survivor spaces, and then may eventually take them forward. Here's where our collectors can help us out again. So things that are surviving for a while will tend to be shared more. We can end up with using our NUMA memory in a more efficient manner. We can also compact our objects by moving them together, keeping them into the same operating system pages, and we can benefit from the TLB. And there's some really nice stuff we can do in memory. If they live longer than that, they end up being collected into the old generation, which was the tenured space where they get managed in a different way again. And there's some quite cool things we can do even at that level. Like we can make sure things are nicely compacted again into the same regions, and we can do things like string deduplication. So a feature we now have in G1 is we can get it to find strings in our applications that are the same string, and it's incredibly common that we use the same string in many places. It will deduplicate them, so it'll only keep one copy of the character array that's underneath that. That can save us quite significant memory in some cases. It's not turned on by default. It's worth experimenting with some of these things for ourselves. So what happens when we collect? So let's say this is our young generation. We're going to go through a garbage collection phase, and these are the objects that are still referenced. And this could be like an array list or a hash map with pointing to a bunch of other objects that's in there. Well, when we collect first, our garbage collector does what's known as a depth first copy. So it finds all of the children first and copies them to the new region. So this may be the new survivor region that's in there. It may be a new region in the old generation. And then it'll copy the parent structure that pointed to those. Now this is nice because we put all of this memory together. We put it into the same operating system pages within the same cache lines within the CPU. This can give us a lot of memory benefits. Like we've seen the randomly walking around and also sequentially going through memory start giving us a big difference. So garbage collectors do have a cost, but they also bring some benefits, and it's worth weighing them up. So we don't get them for free, but they also help pay their way in some interesting ways. They have this bit of a problem, is that many of the algorithms have to stop the world to do things in a sensible way, and this becomes a major issue. It slows down our applications. It makes us subject to Amdahl's law and universal scalability laws. We bring all of those threads to a stop. So some of the collectors try to make that pause time as short as possible. G1 is doing this by, let's break the problem up. We have a problem. How do we deal with it? We break it up into smaller chunks and eat the elephant one bite at a time. And so what we do here is we split our heap up into a number of regions, typically 2048 different regions of varying sizes that are powers of 2. And some of them are the old Eden, some of them are Survivor, some of them are old gen, and they just repurpose them like that. If you've got a really large object, it has to join multiple regions together to create what is known as a humongous object. And so what it does is it tries to collect as much as it can from a region that has the least amount of objects that are still alive in it. That's what's called garbage first. It's looking for regions in the heap that has the minimum number of objects that are still referenced and still alive. And then it will collect those. It's not the only collector we have that's starting to address this. Like, by far, one of the better ones is Azul Zing C4, where it does truly concurrent and compacting of memory in the background all of the time. You don't get the GC pauses with this, and you get the other nice benefits of it's constantly compacting your memory, keeping it all together, and giving you nice memory access benefits for your code, and makes it work really well. So let's say we were going to compare native memory management and GC. It's really hard to pick a clear winner because there's costs on both sides. So if you've got managed runtime with GC, we have to think about what is the GC implementation. They're all not equal. They're not even remotely equal. Some are much better than others. And they all come with some costs. And the amount of costs vary. So like at a minimal level, we'll have this thing called card marking. And card marking is a way of working out which regions of our heap have references that have changed that we may have to go and look for objects that need to be retained. Because it doesn't want to scan all of memory all the time. So when you're writing objects and you're putting a reference in one object to another object, it's got a bit more cost than you think. It has to mark a card table as well as set the reference in the object. Also, when it comes to writing those references and sometimes reading those references as well, as they come with read and write barriers, and some of them more costly depending on which garbage collector you're dealing with. So things like the parallel collector, this is incredibly cheap. It's a very simple implementation. We go to something like CMS, it gets a little bit more costly. We go to G1, it gets a lot more costly. And this is part of the reason why you get a reduction in throughput in G1, because the cost of writing your references to your objects has gone up quite significantly. Plus, it's got quite a few data structures in the background to keep track of everything that's going on. You get shorter long-term pauses, but you pay a cost in having more work as you go. With something like C4, you tend to not see so much of these costs, but you pay a cost in needing more memory for it to run quite well. And you need the CPU and the memory for doing this in the background. Well, what's it like on the native side? Well, all malloc implementations aren't equal. There's a significant difference in the performance and characteristics you get out of them. You may go with your standard runtime, but there's other cool and interesting allocators out there that do better than some other allocators. So JE-malloc being a good example of a better one that's out there. But the big elephant in the room when it comes to local allocation is what happens when you pass memory from one thread to another. This is the really hard thing that we deal with. And actually, the real truth with objects and their allocation or memory in general is not the allocation, it's the reclamation. All the costs come when you go to collect, much more than whenever you allocate in the first place. Like our allocators in the managed runtime are quite fast. We pay a cost for the collection that's quite significant. Same in the native world is we can allocate quite quickly, but we often have to pay quite a cost when we reclaim them, particularly if we reclaim across threads. And we get things like we don't benefit from the compaction. We don't benefit from the way the garbage collector keeps our memory much neater. We end up with fragmentation and all sorts of other problems on the managed side. But kind of where next for GC and what's coming with this? Like, with GC, we can start looking, well, could it organize memory in the same way as it starts organizing code? It can do some nice things to make our code faster by laying it out in different ways, by doing different stuff. Could it do the same thing for our objects? Like, what if we are doing nice design and we're doing something like DDD and we're modeling stuff with aggregates, and aggregates should all be treated together and kept together? We could benefit from that. Well, there's quite a bit of experimentation going on at the moment. There's looking at inlining aggregates together, and it keeps them together in memory, but also makes them available at predictable offsets so we don't get the data-dependent loads. A lot of the research that's coming out of this is showing significant benefits to our code. Doing this in native languages is nice, and you can get a good instinct for it, but you don't guess everything. I've seen one piece of research in this recently where people were making assumptions about, well, if I could apply some automatic inlining to, say, a hash map, what would give me the right results and what would give me the best results for dealing with this? And what was discovered was if you inline, you don't get the benefits from the leaves so much, you get the benefit from the trunk of the tree in the first place. And that was a surprise, because it turns out we use hash maps all over the place. And inlining the hash map into the parent was actually more important than inlining the children into the hash map. Measuring things for real starts to show a lot of this up. So where does some of this go? And what does it end up sort of paying out for in the end? I kind of ask an interesting question here is, what is the most important thing we need to achieving good performance? Anybody got any ideas? Money? Measure, yeah. Technique, but it's not the only thing. Anything else? Yes. Having a target. Well, it lets you know when you're done, but it's not the most important thing to achieving that goal. What's the most important thing you need to achieving that goal? Repeat it. Yeah, that plays into it a little bit. I'll argue this is the most important thing you need. Time. To do anything well, you need time. Like, how many of us work on a project where we say we've got too much time? Doesn't typically happen. I love this quote, and I think it is so true. If I'd had more time, I'd have written a shorter letter. This applies so much to writing code. Like, you come back and you revisit, you refine. having the time to measure, having the time to have repeatable experiments, having the time to build on good foundations, it makes such a significant thing. Like, performance people will give you a list of all the things that really matter, like avoiding duplicate work. Like, this is one of the classics. If one language is 5% or 10% or whatever faster than another language, but you do the work twice unknowingly, you're just blowing the whole thing. Like, being aware of some of these things. Like, I won't go through the list, but it's kind of really interesting. These are the things that matter. What matters is having the time to do it. And it's really difficult to do it in a large code base and do it very, very well. Like, in the keynote yesterday, Todd and I talked about Aeron and a little bit of what we discovered. And it was really key that we had the time. So why did we choose to do it in Java first and then ported it to other languages later? What was a surprise the first time we did it, more than anything? It's like when we developed the first cut of it in Java and the first cut of it in C++ and the first cut of it in C#. The time to get to it working was interesting. Java is probably the fastest language to get to a working version. It was also probably the fastest language to get to a version that's actually reasonably quick as an implementation. Now, you can revisit, you can refine, you can make it faster afterwards, and ultimately you can make the C or the C++ version faster than the Java version. Kind of interestingly with the C# as well. But for the same amount of time, you get to a much faster implementation of something using the managed language. And we found that actually the algorithms matter way more than the details of the implementation. That becomes a refinement at the end. The big jumps come from the design and getting the design right and having the right algorithms. And you need the time for that. Like, it's not the only example. I interviewed the C# team last year for some other work I was doing. And the Roslyn compiler was an interesting step for them. C#'s compiler was written in C++ until Roslyn, where they decided to rewrite the C# compiler in C#. The team did not like this to begin with. They kicked, they screamed, they didn't want to do it, and they eventually did it because they were forced into it. A while later, they were actually quite surprised. They ended up really liking it. The good thing is that actually forced them to improve the language quite a bit. So kind of a good argument for like the Java compiler, the JIT compiler should be written in Java would be a good way to force it to be better. And it'll make things a lot nicer. But now they've got a new compiler that's faster and more functional and easier to work with, and it's written in C#. And you start thinking, well, where do you spend your time? Well, you start looking at, I think this is sort of the pyramid of things that you really need to care about. It's like, what are the models of what you're dealing with? You need a good model of how we deal with stuff. We need to use the right codecs. Like, we spend so much time turning stuff into XML and JSON. Like, if anybody says they care about performance and you use XML or JSON, you're lying to yourself. Get over it. It's just a terrible waste and a kind of wrong thing to do. Like, then what algorithms, what data structures, and do you use the hardware in the nice way? Like, do you really understand how a network works, how a disk works, how or CPUs even work and memory works? Like, picking the right things really matters. And the good thing that comes out from things like GC is we get access to some really nice new data structures and ways of working with concurrency that's just very, very difficult in that world. So, kind of wrapping up quickly, and closing, I've got a kind of interesting thing. It's like, what does the future hold? Like, if anybody here is old enough to remember these arguments, remember the arguments about should we write stuff in assembler or C++ or C? I know people who work in the games industry and I remember these arguments being made all of the time. And what people started finding out was that on a large application, you couldn't beat the C++ or the C compiler. You could for small parts of it, not for the big one. Now here's something to think about. This screen is a number of floors high. It's interactive. You can touch it and deal with it in real time. What language do you think that's written in? Java? Someone actually got close to it. Someone said Scheme. It's not actually Scheme. It's a language called Impromptu, which is a derivative of Scheme that's been done in Brisbane in Australia. It's got a real-time garbage collector. It's effectively Scheme with some nice intrinsics, and you can do incredibly cool stuff like that. If you can do something that's a number of stories high, that's real-time interactive and that, we can surely do web pages. and do it better. So let's think, we don't have infinite time. Where do you spend it? And kind of think carefully about it. It's a kind of interesting world going forward. So thank you.